Okay, welcome back. We're going to talk about section 2.4, and we're talking about the something of a matrix. And I'm not going to tell you yet what we're talking about. I want to hold off on that. And an important application from this section is cryptography, which when I think of secret agents, I think of spies, and whenever I think of secret agents and spies, I think of Perry the Platypus. So this is kind of a fun application of some ideas we're talking about today. So to start things off, you get the following secret code. Okay, so here it is. It's this list of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 numbers, and it's some sort of message, and we want to be able to figure out what this message is trying to tell us. But from what we see right here, it's just a bunch of numbers. Well, luckily, along with this series of secret message numbers, we also get a decoding matrix. And this is our decoding matrix, and this is all you get. You get this long string of numbers, and along with it comes what you know is a decoding matrix. So what would you do with this secret message? You know, how would you try to interpret it? Say these are the only two things and somehow the instructions got lost. What kinds of things would we try to decode this message? Well, this is truly a mystery. We don't really know what we're supposed to do, but we can just go through a series of trying different things. We do notice that this is a 3 by 3 matrix, right? And a minute ago we counted these guys, and we came up with that there were 15 different numbers. So a 3 by 3 matrix and 15 different numbers that somehow need to be decoded. So maybe there's something to do with the idea that 15 is divisible by 3. You know, operations that we know how to do with matrices, we can add them, we can multiply them by a scalar, we can multiply two matrices together. So one idea I have is we could take these numbers here and throw them in a matrix, and maybe multiply it by this decoding matrix somehow, and out might pop out some more information or an uncoded message. So knowing that this is 3 by 3 here, and knowing that we have 15 elements here, couldn't we make a matrix out of these elements that is able to be multiplied by our decoding matrix? Let's see, with the rules of matrix multiplication, it would have to be 3 by something. We have 15 numbers in the secret code, so probably we could throw them all into a 3 by 5 matrix and maybe multiply it by this decoding matrix. Let's try that. Okay, so I'm going to put these numbers in, and I'm going to put them in as just throw them in one column after the other, and I should end up with 5 columns. Now I have my secret message in this matrix that can be multiplied by our decoding matrix. We could multiply all this by hand, but let's use our calculator. And the important menu that we want to access is this matrix menu here, which you've been accessing all along, and so we always use second matrix. And really all I need to do is go to my matrix menu. I've got the ability to enter new matrices just through the edit menu. I'll enter these two matrices that I'm dealing with and then just ask the calculator to multiply them. So we'll go to matrix A, and we need to enter a 3 by 3 matrix. So 3 by 3, and then we'll start putting in the entries, which is 1, 0, 1, 4, 4, 3, and -4, -3, -3. Okay, just double check that I got it all in. This is my decoding matrix. Looks good. So I'll exit out of there, second, quit, and go back and put in my other matrix, call it matrix B. And this one is a 3 by 5 matrix. And I'll start entering that other matrix, -169. Okay, and I've got that other matrix all entered, and I look at these numbers and whoa, we did not want to have to multiply those by hand. So it's good that we're using a calculator. Okay, let me get out of here. We'll quit. And we're just going to take, what we're going to do is call up those two matrices. So second matrix, and I'll get matrix A. And then I'll just use the multiplication of my calculator, and I'll go back and get that other matrix, matrix B, and hit enter. And this is it. This is the decoding matrix times that secret message matrix. And so then I've got my matrix that my calculator got for me. So I took this decoding matrix, I had this secret message matrix, and I got this decoded message. Well, sort of. This still makes no sense to me. I don't know what the message is, but these numbers actually do look kind of different than these numbers. These were all over the place. But these, if you look at them and you think about our alphabet, you could probably come up with the decoded message yourself. So we're going to pause here for a minute because we need to develop some theory of some of the ideas we're talking about. So we'll say this is a decoded message almost. And we'll pause here to now go develop some theory. So say I have this 2 by 2 matrix A. Say that to matrix A, I tag along, just stick right next to it, the identity matrix. This is the 2 by 2 identity matrix. Once I stick it on, I'm going to put this new matrix, which is a 2 by 4 matrix, through RREF and just see what I get. So I'm going to put that in my calculator and perform reduced row echelon. And once it goes through reduced row echelon form operation, this is what spits out. And interestingly, we had a matrix tagged on with the identity matrix, and once I put it through reduced row echelon form, I get the identity matrix and then some other matrix here. So I can think of this as, this is the matrix A matched up with the identity matrix of size 2. And it went through RREF, and what I got out was the identity matrix of size 2 and some other matrix. We'll call it A star. It's somehow related to A. It's definitely not A, but we want to know what's the relationship between this guy and this guy. Okay, and I have another matrix, B, which is a 3 by 3 matrix. I'm actually going to put it through the same process. I'm going to tag on an identity matrix, put it through RREF, and see what comes out. And I haven't even told you why the heck we're doing this, but these two steps, in a minute, we'll see that they yield something that's pretty powerful. So to this matrix B, I'm going to add the identity matrix of size 3 by 3. There we go. And I'll ask my calculator to put it in reduced row echelon form, and I get this guy out. Again, the identity matrix shows up in the reduced row echelon form of this new matrix. So here I had matrix B with an identity matrix, a 3 by 3 identity matrix, and what spits out is actually the identity matrix of size 3, and then B, not B, but we'll call it B star. Okay, let's do one more. Okay, same story. This time I have this 3 by 3 matrix C. I'm going to put it down, and right next to it, the identity matrix of size 3 by 3, and I'm going to perform this reduced row echelon form. And once I do that whole big long process, I get this. So for the first time, we're actually not getting the identity matrix as that first part of the reduced matrix. And this sometimes happens in this process. So here we didn't get the identity matrix of size 3, and we actually don't even care what else happened, because once we see that we don't get that, this part here is not any help to us. So we're going to hold on to everything we've done here for a minute, and we're going to remember, we're going to call A star this part of the matrix that we got after doing this whole process. And similarly, we'll call B star this part of the matrix that we got out of this big long process. And we know there was no C star. It didn't exist. We came up with, the problem was we never had an identity matrix on this side over here. So C star does not exist. So hold on to all of this in your heads, and we're going to talk about something in real numbers for a minute. So remember, in real numbers, you can take 5 times something and it equaled 1. And we know that this something is the number 1/5. So 5 and 1/5 are inverses of each other, multiplicative inverses of each other. So 5 and 1/5 are inverses of each other. And we could write this, we know that 5 to the negative 1 is 1/5, right? So you could write this as 5 times 5 inverse equals 1. And for any real number, you can find its inverse. So for example, if we had 4/3, you know, what times 4/3 would get us back to 1? Well, its inverse is 3/4. And so 4/3 and 3/4 are inverses. So this is great. This is how it works out in real numbers, and you can always find a number's multiplicative inverse. We're not really dealing with real numbers, we're in matrix algebra, so let's see how this might correlate to matrices. Okay, so still holding on to this example here with A and B, where we went through this big long process and found these things called A star and B star. What I want to do now is find what happens if you multiply A star by A. Or the other way, what if we multiply A by A star? You know, what is this process here really finding? And let's find this one first. So I'm going to take A star, and I'll multiply it by A, and I get, let's see, 1 times 4 is 4, negative 1 times 3 is negative 3, so 4 plus negative 3 is 1, and then this row in this column, I get a 1 plus a negative 1, that's 0, and then I get this row in this column, negative 12 plus 12 is 0, and this row, this column, negative 3 plus 4 is 1. Okay, so we get the identity matrix back. Let's try the other guy. So I'm doing a multiplication again. This time I'm just going to reverse the order and take A times A star. And when I go through that, I get 4 plus negative 3 is 1, and negative 4 plus 4 is 0, and then 3 plus negative 3 is 0, and I get negative 3 and plus 4 is 1. Yes, we get the identity matrix again. So what is this A star? Whenever I multiply it by the matrix A, I'm ending up with the identity matrix, either way I do it. And the identity matrix is like what the real what 1 is in the real numbers, the identity matrix is in matrix land, matrices. And so this A star is, I mean, I know you guessed it already, this A star is just the inverse of the matrix A. So it's another matrix that is A's inverse. So A star is, in fact, A inverse. And what we'll find if we do this multiplication, B times B star, do all of this, and you'll come out with the identity matrix. A 3 by 3 identity matrix this time. And same story for B star times B. That will give us the identity matrix. So B star is the inverse of the matrix B. So B star is the inverse of B. And do you remember that matrix C that we were talking about? This matrix, we put it through this process and everything broke down. So we learned that C star didn't even exist. So the matrix C doesn't even have an inverse matrix. This is different than real numbers. Every real number has a multiplicative inverse. But in with matrices, sometimes certain matrices don't have inverses. So some matrices will not have an inverse, and that's an important idea. Some matrices are invertible and some matrices are not. Let's now give a formal definition of a matrix inverse. We start with a square matrix, so A is an n by n matrix. And to even have an inverse, a matrix has to be a square inverse. You can't have an inverse matrix if you're not. So this is the number one condition. So it must be a square matrix. So if there exists a matrix A with a little -1, we'll read this A inverse, such that A times A inverse is the same thing as A inverse times A, and both of those have to equal the identity matrix of size n by n, then we say that A is invertible, and A with a little -1 is the inverse of A. So if these conditions are met, then we say A is invertible. It's a big deal. And A inverse is the inverse of A. If these conditions are not met, if there's no such matrix that makes this happen, so if no matrix A inverse exists, then we say that A is not invertible. Okay. So this is a big idea, this idea of invertibility, so we want to make sure we get the stars there. And then finding the inverse of a matrix, you guys could probably teach this part because we're basically just going to do this process right here. So what were the two steps? Do you remember? The very first thing we did to a matrix was we adjoined this identity matrix. And then the only other step really was to put it through the process of reduced row echelon form, and we found that when we did, we get the identity matrix and then this special matrix, which turned out to be the inverse of A. So really just a two-step process here. So we'll, list out that two-step process, but I should say at this point that there are actually other ways to find the inverse of a matrix. In a little while, we'll learn something called the determinant, and there is a way to find an inverse using the determinant. But for right now, the process we're going to use is using Gauss-Jordan elimination. So using Gauss-Jordan elimination, putting that matrix, that special matrix in reduced row echelon form. So the very first thing we do is we adjoin the identity matrix to A. We get something that looks like this. The matrix A, and then stuck right with it in the same matrix is the identity matrix. And then we're going to find the reduced row echelon form of that, those two matrices adjoined, this new matrix. And there are two possible things that can happen, and we saw both of them. If we perform that reduced row echelon operation and we get something that looks like this, some new matrix B shows up, but in the beginning of the reduced matrix we have an identity matrix, then this new matrix here is our inverse matrix. So then whatever shows up over here is our inverse. That everything works out great. A is invertible. But if we go through that whole process of joining the identity matrix to A and then putting it in reduced row echelon form, and we get something where the beginning part is actually not the identity matrix, then I don't really care what's over here, because at that point I know that A has no inverse matrix. Okay, so in this case there would be no inverse matrix. So this is the definition, and then this is one of the processes, the first way we'll learn to finding the inverse matrix. So we'll give this guy a red box to indicate that it's special too. It's an important thing to remember. Finding the inverse of a matrix gets the red box. The definition, we're going to give it all these stars. So these are two things that we definitely want to remember. The invertibility of matrices is a big deal in linear algebra. And there's two things I want to just re-emphasize. We've already mentioned them, but two ideas to remember with the inverse. So first, square matrices only. This only can happen when you're talking about a square matrix. And can you think of what the second important thing I would want to emphasize here with A inverse is? I'm sure you guessed it, but the idea that it doesn't always exist. So we'll get a little practice with this process. Our first example, find A inverse if it exists, and here's our matrix A. So I'm going to adjoin the 2 by 2 identity matrix to A, and then I'm going to make it all one big matrix. Then I'll put it through the reduced row echelon process and see what my calculator spits out. And this is what I get out. And so I know that this is A inverse because I have an identity matrix right here. I'm going to do just a quick check on this. So to check that I didn't make some error somewhere, I'm going to take this A times what I found for A inverse and make sure I'm getting the identity matrix back when I multiply them. So here, this row and this column, I'll get 0 times 1 is 1. This row and this column, I'll get 0 plus 0 is 0. And this column, no, this row and this column will give me -3 plus 3, that's 0. And this row, this column will give me 1 plus 0 is 1. Definitely checks out. This is the inverse of A, and I found it with our process. Okay, one more example like this. Let's take this 3 by 3 matrix and find its inverse. So I've done the first part. I've taken the matrix C and I've adjoined the identity matrix to it. And then I'm going to ask my calculator to help me find the reduced row echelon form of this. And once I go through that process, this is what I get out. And looks like we have some kind of long numbers here, which in and of itself is no problem. These are just some sort of, non-integers. That's fine. The problem is, though, that this first part here is not the identity matrix. As soon as we know that this is not the identity matrix, we know that the original matrix here could not be inverted. This is not invertible here. So this right here indicates to us that there is no C inverse, because this should have been, if there was, this should have been the identity matrix after we went through this process. So because this part isn't the identity matrix of size 3, then C inverse does not exist. So we've seen an example where it was nice and easy and just popped out, and then this guy where the inverse matrix just didn't exist. We should go back at this point and say this was the thing we were going to talk about, is the inverse of a matrix. And we definitely still want to finish this example. We'll come to that. We still need to develop a little bit more theory, though. Now there are some properties of matrix inverses that we want to talk about, and we're going to use them to help us solve some problems. The first one is, if you have A inverse and you actually want to take the inverse of this, what should this equal? The inverse of the inverse, that actually gets you right back to A. And this follows from the definition of matrix inverses. So this is because the inverse of A inverse is the thing that will take you, it's the thing that will multiply by A inverse to get us back to the identity matrix. And the thing that multiplying by A inverse gets you back to the identity matrix is just A. So this is A inverse's inverse matrix, and you could do it either way, on the left or on the right, and it stays like that. The second property we're going to look at is, say you had some scalar multiplied by a matrix, and you want to find the inverse of that. If I want to find the inverse of CA, I have to think of something that will multiply by this whole thing and get me back to the identity matrix. And I know I can get pretty much close by multiplying by this. So then I would have C times the identity matrix. Well, to get, this C to become a 1, I need to then multiply by 1 over C. And so this right here becomes the inverse of CA. We know that we can pull this scalar, this constant, out front, and we can just call it 1 over C times the matrix A inverse. So the inverse of this matrix inside the parentheses will be 1 over c times A inverse. This is the piece of the puzzle that when we multiply it by this guy inside the parentheses, this will get us back to the identity matrix. I know this looks like just tons of notation, and is there really any significance to it? And it really is. There's some reasoning behind why, what all of this means, that the inverse of this matrix in the parentheses needs to be this expression. The third property has to do with the idea, if I have two matrices that are being multiplied together, and I want to know what the inverse of that product is. So the inverse of this product should be something that when I multiply it by that product, I get back to the identity matrix. And the thing that should work is this times this. And what happens is these two collapse into the identity matrix, and then, so that's gone, essentially. And then the A and the A inverse will collapse into the identity matrix. You want to think about why it can't be this. It's definitely not this. It's not the inverse because multiplication in matrices is not commutative, so we can't just swap things around, you know, oh, I'll just reverse this order and then they'll cancel. You definitely can't do that. So this isn't going to work. You have to be really careful with the order, and you would know that these two would create an identity matrix. They're right next to each other, and then this and this will create an identity matrix. So this this guy right here, this is an important one to remember. The inverse of a product will be the product of their inverses, but we need to make sure that it comes in this order. Okay, number 4, if I have the matrix A and I have a bunch of them multiplied together, so the powers, the A to the nth power, and I want to find the inverse of that, this is just going to be the inverse of A n times. So you just think about, you've got a big long string of these ANs all multiplied together, and you're going to knock out each one back to the identity matrix one by multiplying by a series, n of them, a product of A inverses. And the last property we need to talk about is, okay, you guys remember what this guy is. It's the transpose of A. That's where we're swapping rows and columns in A. And say we wanted to find the inverse of this. The inverse of the transpose is actually the transpose of the inverse. This one falls straight out of the properties of how transposes work. Okay, knowing these properties of matrix inverses, this is a situation we're presented with. So if A inverse equals this, they ask us to find what A is. Okay. So we've got a few things going on here. We have a constant, a scalar out front. That leads me to believe we'll probably be using this somewhere along the way. And we don't know A, but we do know A inverse. There's no product going on here. There's no powers of A, and there's no transpose. So we probably are going to use these first two properties. And for sure we are. This first property tells me that the inverse of an inverse the inverse of an inverse function is not function. The inverse of an inverse matrix is back to the original matrix. So what if we found the inverse to this guy? We would find A. And this is a matrix that we can find the inverse to. We'll use the second property and our strategy for finding inverses. We remember that A inverse inverse by this first property equals A. This is actually the thing we're trying to find, so we'll just go ahead and find the inverse of A inverse. The first thing I'm going to do is take this part of our matrix, and I'm going to find the inverse of this. And so I'll take that, I'll join the identity matrix to it, and then put it through reduced row echelon form. And this is the matrix I get out. So this was good. It has an inverse matrix because this is the identity matrix, and this is at least the first part of it. So when I said this is part of it, this is not the final answer, because though we found the inverse of this part of the matrix, this is still part of A inverse, so we have to deal with this. And we know that to find the inverse, when we have a scalar out front, we need to take the reciprocal of that scalar. So the only other thing to do is take the reciprocal of 1/3, which is 3. And we've just found our matrix A. So these properties are telling us that if we multiply this by A inverse, we should get the identity matrix out. Let's do a quick check just to make sure what we really found is what we wanted. This is the original matrix they gave us, and this was actually A inverse. And this is the matrix A, so when we multiply all of this together, it should be the identity matrix. And these guys, the 1/3 and the 3, will multiply to 1, so that's good. Those are gone, and we can just focus on multiplying these matrices together. This row, this column, we get 0, and 2 times 1/2 is 1. And this row and this column, we get 3 plus -3, and that's 0. This row here and this column will give us 0. And this row and the last column will give us 1 plus 0, which is 1. And it totally checks out. We get the identity matrix of size 2. So this was the right answer. This was the thing we were looking for. And the way we found it just from this original problem was we used properties 1 and 2 over here, properties of matrix inverses. Here we need to give a little bit of notation. If you see this thing, A to the minus K, we know what that means in real numbers, but with matrices, what this means is it's just A inverse, so the inverse matrix raised to the K power. So here we're given a matrix, and luckily they give us the inverse matrix too, and we're asked to find A to the -2. Well, because of what we just learned about notation, we kind of know what that means. This is just going to be the inverse matrix raised to the 2nd power. So A to the -2 means A inverse, raised to the 2nd power, and that's just, they've given us the inverse matrix, so it's just this multiplied by itself. So, and that's something we can figure out pretty quickly. Don't even need to whip out the calculator for it. We've got 1 plus 3 is 4, and then we've got -1 minus 4 is -5, and then we've got -3 minus 12 is -15, and lastly we'll have 3 plus 16 is 19. And so this is it. This is A to the -2. This next example is actually on your homework. It's number 17. And I just wanted to for us to kind of get started on it together. So it's saying we want to find x such that all of this is true. And all we know is that this matrix, the inverse of this matrix is equal to this. And there's an x in here, and that's the x that we want to find. So how would we go about doing this? I'll give you a couple hints. First of all, this is an equality. So as long as we do the same thing to the left side as to the right side, it stays an inequality. And so my first hint is, why don't you take the inverse of both sides? On the right side, you can definitely take the inverse of that matrix. On the left side, you think, oh, how do I take an inverse of something with an x in it? Well, you really don't have to deal with that because the very first property will help you out here. That's my first hint, and then my second hint is you'll get, some things equal to each other. If two matrices are equal, then each of their parts are equal. So any of the elements that match up, you could set equal to each other. And so that's my hint on this example. It's a really good example because it incorporates a few different things that we've learned in the last couple weeks. Okay, one topic we want to hit on is using matrix inverses to solve systems of equations. And here we have a system of 2 equations and 2 variables. And recently we've gotten some practice writing a system like this using matrix algebra. Essentially, we can write this whole system as just this one equation here, ax equals y. And if we do that, if we choose to write it that way, we have to think, what is the a, what is the x, and what is the y? Well, the A is, you remember this matrix, this 2 by 2 matrix, and it's going to be the matrix of coefficients of these equations, and it's not any of these numbers over here, not the constants, but it's just the coefficients on the on the variables. So this is going to be 1, 5, 2, 9. And then we have a vector of constants over here, which is the -1, 3. And then hopefully you remember what this x should be here. If A times x equals y, and we remember how matrix multiplication goes, this times what here will equal this. Should be x1, x2. Okay, so we have in one teeny tiny equation here, and these guys here, all of the information of this system. And when we're solving these systems of equations, our whole goal is to find, you know, what x1 and x2 are. So to find these guys. So wanting to solve this equation for x, can you think of a way that we could use matrix inverses to solve this equation? Well, to solve it, we really want x all by itself, and x is representing this vector here. What if we multiplied both sides by the inverse, A inverse? This would go away, it just becomes the identity matrix, and the identity matrix times x is just x. And then this is something that we can evaluate. So this is the way that we'll use inverse matrices to solve systems. This is just an alternative to Gauss-Jordan elimination. So we'll multiply both sides by A inverse. And this guy here, this just becomes I2. And so we have I2 times x equals A inverse times y. Well, I2 times x, this is a property of the identity matrix, that this just becomes x. It is the multiplicative identity. So x equals A inverse times y. And so we've essentially solved it as long as we can find out what A inverse is. So I'll take this and go over here and do a little work and find out what A inverse is. Okay, so I did a little bit of work and I found out that this is what A inverse is, and I'll go ahead and use that right here. This is the guy I'm looking for. This is the whole problem, is to find out what x is. I already know. So we can say that x equals -9, 5 to -1 multiplied by the vector y, which is -1, 3. And we'll do this multiplication super fast. 9 plus 15 is 24. And -2 plus -3 is -5. This is our solution to the whole system of equations. This is what the vector x should be. So x1 is 24 and x2 is -5. And we could double check it. We could go back to the original system and make sure those numbers work. Let's see, 24 minus 25 is -1. That works. 48 minus 45 is 3. That works. So we found the solution, and we found it a way that we've never found it before, using this inverse matrix. So in general, we can say if ax equals y is a system of linear equations in n variables, so these are representing matrices and vectors here, and A inverse exists, then x equals A inverse y. So we've just used the inverse matrix to solve a system of equations. The next great thing we get to talk about are elementary matrices. Say that we had some random matrix and we wanted to swap rows 2 and 3, and that's something that you're often doing in, when you're using Gauss-Jordan elimination, is swapping rows. But now my question is there a matrix that we could multiply by, with this matrix and perform that operation? So if we want to swap two rows, could we, multiplying by a certain matrix, do that? And we could think of whatever matrix it is, we want to keep this guy the same and just move this one down and this one up. So the matrix I want to end up with is this one. 2, 0, 5. I've just swapped the two rows. So just thinking about what would go in this first row here. When it gets multiplied by this column, the only thing we want it to pick up is this. And when it gets multiplied by this column, the only thing we really want it to pick up is this. And when it gets multiplied by this column, the only thing we want it to pick up is this 2. So probably something that looks like this. This would achieve what we wanted to achieve. This times the first column gives us 1, and then it'll give us -1, and then give us the 2. That's perfect. That's just what we need. Okay, this next row, what we really want to do is we actually want to pick up this third row. So think about taking this row and operating it with this first column. We don't care about this guy, we don't care about this guy, but we want this guy. So how about something like 0, 0, 1? Let's run that through the second row and see if that's what we get. Or I'm sorry, let's run the second row through all these columns and see what we get. So this operated with this would give us the -1. Perfect. This operated with this would give us a 4. Perfect. And this operated with this will give us that 3. Okay, it did just what we did. And you can probably guess already what that last row needs to be. What this will do is pick up all those middle elements and put them in the third row. This is the matrix that we want to perform that elementary transformation. So we call this an elementary matrix because it performs one of those 3 elementary row transformations that we were talking about the very first days of class. Can you think of how you could create a matrix that would multiply a constant through one of the rows? So say we wanted to take the same matrix and multiply row 3 through by 7. That would correspond to one of those other elementary row transformations that we talked about early in the semester. If we want to have a matrix that multiplies just this third row through by -7, we really want to keep this row and this row the same. So probably we would have something like 1, 0, 0, because that's just going to pick up the first elements, and 0, 1, 0 here, and that'll pick up the second row of elements. And then what should we have for this third row? Every time it operates with these columns, we want it to be, just to ignore these guys, so we probably want zeros here and here, but we want it to multiply this by 7. And so just knowing that, it's pretty obvious that this needs to be 7 and the others need to be 0. So this is it. This is a matrix that does that operation. So for the first time, we're seeing the signs of how matrices can be these types of transformations, that they take a matrix and do some sort of, almost like a function, like they're doing some sort of changing of this matrix into something that we beforehand knew that we wanted to do. Another elementary operation we might want to do is add 2 rows together. And this time we're going to add row 1 to row 2, but we're going to keep row 1 as it is and keep row 3 as it is. And we want to add row 1 and row 2 and put it in the row 2 spot. So we would get 3, -1, 7. And the big question is, how do we find a matrix that will do that work for us? Well, like these old examples, we need to keep rows 1 and row 3 the same. So we probably would want the top row of this transformation matrix to look like that, and the bottom row is just going to keep row 3 the same. The real question is, what is going on here? And this one we're going to leave as a question for the quiz. So what we're seeing in these examples is the work that these matrices are able to do these elementary row transformations to the original matrix. So this is a big idea, that elementary row operations can be performed through multiplication with these special elementary matrices. look a lot like the identity matrix. Not entirely. This guy is a little bit different, and we'll find that this guy is a little bit different, but lots of ones, lots of zeros. You're just picking up the things that you want to pick up and maybe multiplying by certain constants. Okay, let's get back to the example that we started this section with, this cryptography, this secret message that we were able to decode. We had received this secret code, and we also got a decoding matrix. We didn't know what to do with it, but we decided this was a 3x3 matrix. There were 15 numbers here. We would somehow combine those in a matrix multiplication, because this is a linear algebra class and we've been talking a lot about matrix multiplication. So we took the decoding matrix and we multiplied it by this secret message matrix. And this is what we got out. And we kind of stopped there. Well, look at these numbers. All of these numbers are 27 or below. And 27, if we think about the number 26, that's definitely a significant number regarding secret codes, because there's 26 letters in the alphabet. So let's just start trying to think of what the letters are that correspond to these numbers. So second letter of the alphabet is B, 21st is U, 25th is Y, 27 I don't know what that is because there's not 27 letters in the alphabet. The ninth letter of the alphabet, I, we get another B, 13th is M, don't know what 27 is. And I know the 19th letter is S, T, O, third letter is C, and 11th letter is K. Okay, awesome. I just got this secret message to buy IBM stock. And so you can see how somebody could send you numbers, and if you knew the decoding matrix, maybe they didn't send it with you, maybe you already knew what it was, that you would be able to find out exactly what they were trying to tell you without anybody who intercepted all this. Well, they would just intercept this. They wouldn't know what the heck they were talking about. And so this is the idea of cryptography, that you're going to take a message and sort of make it secret in a way, a numerical way, and the person receiving it has a way to decode it. And this is all about, this actually is an inverse matrix of the encoding matrix, and we just, this is an inverse of the encoding matrix, so we call it a decoding matrix. So the idea is you have a message, and then you're going to encode that message with a matrix. Then you're going to send that secret message, and somebody on the other end is going to receive it. And then they're able to decode it with the inverse of the original encoding matrix. And they can receive the message. So the beauty of this is, once it leaves the sender's hands, it's in a form that nobody else can interpret. Nobody knows what the heck these numbers mean. But once it's in the hands of the receiver, who knows how to decode it, then the message can be decoded. And you know all the applications of this. This was a big deal in World War II. It's, I'm sure, still probably a big deal in military things. In this example, I want to encode the message River Kwai with this encoding matrix. Of course, you can pick like a million different types of encoding matrices, and that's what makes this whole cryptography so beautiful, is the person that you're trying to keep it a secret from, they have no idea what the matrix that you're encoding it with is, and there could be, a million billion possibilities, and the larger the matrices that you're encoding it with, it just gets more and more complex and really difficult to break that code. Okay, we want to encode this matrix. So the basic idea is we're going to think we have this message matrix. We're going to put this message numerically into a matrix. And then we're going to use this encoding matrix that I have. And I'm going to send this. This is going to be some secret message matrix. And once the person receives that secret message, they're going to then multiply that matrix by the inverse of the encoding matrix or the decoding matrix, and what they'll get is the original matrix back again, or the original message matrix back again, and they'll be able to know what the message is. Okay, so our job is to encode this message right here. Okay, so I've just taken this message and given each letter a number. You know, R is the 18th letter of the alphabet, I is the 9th letter of the alphabet, V is the 22nd. But I can't just send these numbers. I mean, that's like not a secret code at all. Any fool could break that code. That's the code we were using in elementary school. So I need to take these numbers and I'm going to use this encoding matrix. So I'll take this message and I'll multiply the encoding matrix with this message. And that's the thing I'm going to send to my secret agent. So I've got my encoding matrix here. I'm going to multiply it by this message. I had to use a few 27s for the space, and at the end I needed some fillers, so I used some 27s there. And so this is it. This is the matrix that carries the secret message. And this is the one that I can send across the ocean and not be afraid that anyone could detect what I'm trying to say. So to make it even more confusing, I send it as a big long string of numbers. They don't even know that it goes in a matrix or what size matrix it goes in. This is the message that I send across. This is the secret message. So here's this secret message that I send, and my compatriot, whoever I'm sending it to, my fellow secret agent, he or she has the decoding matrix, which is the inverse of the encoding matrix. So they are going to take this secret message, and remember this is the encoding matrix. So if I take the inverse of this matrix, I'm going to get the decoding matrix. And the inverse of this encoding matrix is this one right here. I just had my calculator figure it out for me. This is what the recipient needs to use to decode the secret message. We'll multiply the decoding matrix by the secret message, and we'll call this E-1 because it's the inverse of the encoding matrix. And once I do that, the recipient is back to the original message. This is the one that they can just read off. They know that this will say River Kwai. So it went through all of that travel encoded like this, and from the encoding matrix and the decoding matrix, only the sender and the receiver are able to tell what it was saying. The big ideas that we saw today, biggest ideas, talking about the idea of inverse of a matrix. We looked at the 5 properties of a matrix inverse, using inverses to solve systems of equations, elementary matrices, and this great application having to do with cryptography. Really big ideas, lots in this section.